Welcome to section 11.2. We're doing inferences about two means. Dependent sample this time. Last section we were looking at independent samples. And now we get to consider dependent samples. All right, and we're going to be introducing the mean as well. So remember, a sampling method is independent when the individuals selected for one sample do not dictate the individuals to be in the second sample. This section we're looking at a dependent sampling method. It means the individuals selected in one sample are used to determine the individuals in the second sample. And sometimes we call the dependent sample matched pairs samples or matched pairs data. So let's practice this again. We had some practice with this in section 11.1. So let's talk about whether it's independent or dependent. A researcher and associates wants to determine the effectiveness of a new medication in treatment of discomfort associated with a common cold. They randomly divided 430 subjects into two groups. Group 1 received the new medication and Group 2 received the placebo. The goal of the study was to determine whether the mean symptom assessment scores of the individuals receiving the treatment were less than that of the control group. So what's the sampling method? Yeah, it's independent because the sample is randomly divided into two groups. So because it's randomly divided into two groups, we would say that this is an independent sampling method. All right, let's look at the next example. In an experiment conducted in biology class, professor measured the time required for students to catch a falling meter stick using their dominant hand and non-dominant hand for 21 students. The goal of the study, was to determine whether reaction time in an individual's dominant hand is different from the reaction time in the non-dominant hand. All right, so we have a dependent sampling method because the dominant hand, an individual's dominant hand, is matched with their non-dominant hand. So this professor had 21 students and he essentially had 42 samples. For one student, he would look at the reaction time using like their right hand, and then if the right hand was in the study, the same student's left hand was automatically in the study. So in this case, the hands were being matched together. So you can say dependent or matched pairs. Last example. 20 people were selected to participate in a psychological experiment. They answered a short multiple choice quiz about their attitudes on a particular subject and then viewed a 45-minute film. The following day, the same 20 people were asked to answer a follow-up questionnaire about their attitudes. At the completion of the experiment, the experimenter will have two sets of scores. Do we have an independent or dependent sampling method? Okay, so again, the 20 people answered a short multiple choice quiz, they watched a movie, and then they were again asked another questionnaire later on. So in this case, the individuals are being matched against themselves. So it's kind of like a before and after situation, so it's dependent. They're being matched against themselves. Okay, so again with that dependent sampling method, we call it matched pairs. And so when we're looking at the data, we're going to be looking at them as paired data. They're going to have this natural grouping. So the pairs of data values then are going to be compared to one another directly. And how we do that is we use the difference in their numerical value. So we're going to be using the difference in their numerical value. Okay, and then we call it the paired difference. And we use the letter D. All right, so if we were doing the reaction hand time for catching something with our dominant and non-dominant hands, to see if there was a difference, we would use subtraction. Let's say it took me like 3 seconds to do something with my dominant hand, and it took me 5 seconds to do something with my non-dominant hand. So there would be a 2-second difference. So that's what we're looking at here. Okay, so we are going to perform the inference on the differenced data. We're going to be doing our inferential study on the difference data. All right, so let's look at an example. We're looking at a guided example. So I'll just kind of read it to you. You guys can also read it by yourselves. Check in and see if we write down the same things. So the guided example was that a test was conducted to compare wearing quality of the tires produced by 2 tire companies. So the following table gives the amount of wear in thousandths of an inch that resulted from the test. 1 tire of each brand was placed on each of 6 test cars. All right, so what's happening is this car 1, it had 2 different brands of tires, brand A, brand B. The car drove around a little bit, and then the wear on brand A was recorded, and the wear on brand B was recorded. So again, we're going to be looking at the paired difference. If there wasn't any difference in these tires, these numbers should be approximately the same, and we would expect the difference to be around 0. Okay, so we could definitely go through and look at all these differences like that and do it by hand. Alternatively, we can use our calculator. I'll show you in more detail in the next example. If we wanted to use our calculator, we would do our first population, essentially, in L1, our second sample from the second population in L2. And then we can define L3 to be L2 minus L1. So make that note here. In the next example, I'll show you where to do that in your list. Essentially, you're going to highlight L3 and create this rule. But more on that in a bit. But we do have this nice shortcut. So again, now that we have this difference data, this is the column we're going to be focusing on. This is the column we're going to focus on. And we're going to be doing all of our inferential statistics on that. So just using L3 essentially, we can find the mean and the standard deviation by running a 1var stats on L3, the difference data. For now, you can always just put in your numbers too, 8, 1, 9, -1, 12, and 9 if you want to follow along. And from 1var stats, the x bar, I'm going to call it d bar though, is 6.33, and the standard deviation of the difference is 5.125. Okay, so let's say we wanted to prove that there wasn't a difference in wear, that brand A and brand B were equally good tires and there's no difference in the wear. So then again, that would mean that there shouldn't be much difference between the numbers in brand A column and the numbers in brand B column. So we would expect the differences to be about 0. All right, so that takes us to part 2. So we're going to collect data in hopes that showing the 2 brands do not wear equally. So if that's what we wanted to prove, we have to find that data. All right, so we can assume that they do wear equally, so the differences are 0, and then we're going to try to show that they do wear equally. So do the data provide sufficient evidence for us to conclude this? Okay, so we're running a hypothesis test. We have this little assumption. Let's assume that third column is approximately normally distributed. So the population parameter of interest, again, is the difference data, in particular the mean. We want to show that the mean of all of the differences from all the different cars is either 0 or far enough away from 0 to be statistically significant. And we're going to use this notation, mu sub d. Okay, so in this case, no difference in wear is your null hypothesis. So if there is no difference, the first and the second columns would be the same, so the difference would be 0. And then we're going to use the same number in the alternative, and then difference in where just means not equal. All right, let's look at our criteria, our assumptions. Again, we want a simple random sample. Data has to be matched pairs, so dependent sampling. Differences are normally distributed with no outliers. The sample size is large, or the population is approximately normal. So notice, we also forgot n is less than 5% too. So these are really consistent with what we've been doing with our means, right? Our student t distribution. It's the same. Okay, so we're going to be using our t distribution since we're working with the mean. And then there's our t-score, and we have our degrees of freedom. Remember, mu sub d is 0 according to our null hypothesis. So our test statistic, assuming the hypothesis is true, is going to be d bar from our sample, L3, over the standard deviation of student t's distribution. All right. And then level of significance is given at 0.05. All right. So let's turn our page. We already calculated some things in step 3 from our 1-var stats on L3. Our sample size is 6. D bar was 6.33. Standard deviation was 5.125. Again, we got that from 1-var stats. And so that's enough information to calculate our test statistic. Let me write it one more time. So 6.33 divided by, I'll put it in parentheses, 5.125 over square root of 6. And so we get approximately 3.025 standard deviation, or excuse me, as our test statistic. Okay, so again, now we want to know, is this considered unusual? And is it far enough away from the mean? So we have two ways of determining that, our classical approach and our p-value approach. Our critical value for the classical method, we can get that from our chart. And this is a two-tailed test, so there's going to be two critical values since we have a two-tailed test this time. So degree of freedom is 5, and then alpha is 0.05. So this is really going to be a critical value t sub alpha over 2 and negative t sub alpha over 2. So area in the right tail is 0.05 over 2. All right, so we can use all that information, go to our t distribution chart, and find our critical value. And our critical value, I'll write it in red, positive and negative, 2.571. Okay, in this case, notice our test statistic is positive, so it's going to be in the right tail, so we'll use our right critical value to help us determine where 3.025 is. And 3.025 is bigger than our critical value, so we're definitely in the critical region. All right, so T naught is bigger than T sub alpha over 2. So we are in the critical region. We can also do the p-value approach. Again, we have two tails since it's different. So two-tailed means it's the area twice. So we have to look at 3.025 right here. Because it's a two-tailed, we also have to consider it on the other side. So the p-value is really this area to the right of the positive test statistic and this area to the left of the negative test statistic. We only do that for the two-tailed test. All right. And we'll do this in more detail. We're essentially running a t-test on the difference data, L3. So we'll just kind of do a little calculator video magic. I'll tell you what the p-value is. The sum of these two is 0.029. And again, in the next example, I'll show you guys that in more detail. But with our p-value, we compare it to our alpha. And how is 0.02 compared to 0.05? It's less than. It's less than. Okay, so again, in our chart, that must mean that since alpha is less than the p-value, this one in blue, whoops, like that. I'll use a highlighter. Oh, I'll just do this. This is where our alpha is. So this one's alpha over 2, and this stuff in blue is alpha over 2. So we can see the red is smaller than that area. So the p-value is low. The null must go. So we are in the critical region. All right, and then that's your decision about the null. If the p-value is low, the null must go. So we're going to write reject the null. Conclusion is still the same. So there is blank evidence. Since we're rejecting, it means we have evidence to support the alternative, so sufficient evidence at the alpha equals 0.05 level of significance to conclude the alternative. To conclude that the two brands show unequal wear or different wear, something like that. Okay, so that was really a detailed problem. Remember, this next example, when we use our phantoms, is what I want you guys to show on your quizzes and exams. So let's see what that would look like. All right, so now it's the practical problem, what you guys are doing. So a test preparation company claims that its SAT prep course improves SAT math scores. The company administers the SAT to 12 randomly selected students and determines their scores. The same students then participate in the course. Upon completion, they retake the SAT. The results are presented in the following table. All right, so this is match pairs data because the students are paired against themselves before the class and after the class. So this represents like Kathy's score before the class and Kathy's scores after the class. So Kathy is being matched against themselves. And to get any meaningful results, we would look at the difference, right? See if there's any increase in the scores after the course. Maybe it wasn't a good course, and maybe the scores were approximately the same. Who knows? But we have to test that claim. So we're going to test the claim that the prep course improves math scores at the alpha equals 0.1 level of significance. Assume the differences are approximately normally distributed with no outliers. Lovely. Okay, so remember on the quiz and exam, this part will be blank. You guys have to remember phantoms. Because it's matched pairs, we're looking at the mean difference, mu sub d, and it looks like we're doing post-class minus pre-class. So after the class minus before the class. So if the class was good, these should be positive numbers. Big score minus small score. Your hypothesis, we're going to assume that there was no difference in the scores. So that the null hypothesis is equal to 0. And again, since we want to show the course is improving the scores, big minus small is positive. So your alternative is going to be greater than 0. Assumptions. So we do have that matched pairs data. Definitely. Simple random sample. And then it's given that the sample is normal without outliers. So make sure we write that. Okay, and then our calculator function, name that test, is a t-test, just like if it was for a single population. So let's look at the screenshots, or let's first explain this first part. So put the befores, it goes vertically, into L1, put the afters into L2. Okay, so if you guys did it correctly, t-test. The most important thing is figuring out how to get L3 and then running your t-test on L3. Your test statistic is that top value, just as before. Your p-value is right below. And we have two options at this point. The quickest option is to use alpha to compare your p-value, which is a probability, to alpha. And alpha is 0.1. All right, so our p-value is low, the null must go. Alternatively, you can also, it's a right tail test, so you can look into your chart to find t sub 0.1 on your t distribution with 11 degrees of freedom. And you would see that our test statistic is to the right and in the critical region. So both cases say that we reject the null. And our conclusion, and again, it's always the same. So there is, if we're rejecting, that means we have sufficient evidence to support the alternative. We state the level of significance. And then to conclude, we were trying to show that the course was effective, so you can just say to conclude that the prep course improves scores. All right, so let's continue on with our confidence intervals. So we're also going to be creating a confidence interval for the population mean difference, mu sub d. And again, it's always that same format. It's always the point estimate, which is d bar, plus or minus your margin of error. Right, so your point estimate is right in the middle, margin of error is on either side. So we have that 1 minus alpha 100% confidence interval for mu sub d. So to estimate, this is the parameter we're estimating, is the following. Lower bound and upper bound, I'll write it the same. One time we add, one time we subtract our margin of error. Margin of error is always that critical value times the standard deviation, and so it's still that same format, and we're using n minus 1 degrees of freedom to determine our critical value. So let's construct a confidence interval. So it's the same problem again from the SAT scores, but rather than running a hypothesis test, we're going to be doing a confidence interval, a 95% confidence interval for the mean difference of SAT scores. And whenever we do a confidence interval, we panic. So the parameter is the mean of the difference data. You can write it out like this, whoops, difference data, or you can use the symbol, which is mu d. The assumptions are same as before. So we'll just take those from before. Name that test, or interval really. And we're going to do the same thing. We're going to put before in L1, we're going to put after in L2. L3 is L2 minus L1. And then just like if we were doing a single mean instead of two populations, a single population, we're going to use a t-interval. But make sure you put that it's from L3. Okay? Okay, and again, it's important to know, I would make yourself a note that you're doing after minus before, because that's going to affect how we state our conclusion. All right, and then if we run that test, and you can try that out on your own, we get our interval. Okay, and notice, we said it before, when we have two populations, it's important for your confidence interval to see if it's negative, to see if it's positive, or to see if it contains 0. And in this case, notice our confidence interval is positive. It's positive. So I'll make that little note. These are positive. And it's positive because if we're having a difference, it means it was big, and I'll write it up here, minus a smaller value. If it was negative, that means it would be a small value minus a larger value. So that's going to help us when we write our conclusion. So we are 95% confident confident. All right, that. And then the kind of generic way we could write it that doesn't really give us a lot of information is we could say that the mean difference of the SAT scores is between 2.3 and 22.6 points, right? But that doesn't tell us anything. It doesn't tell us any information about the class. So let's be more specific. So we could say that again, it's after minus before. So we could say something like the mean of the SAT math score after the course is 2.3 to 22.6 points higher than before the class. So this gives us more information. So when, again, we're comparing two populations, rather just saying the mean difference is between 2.3 to 22.6 points higher, let's get in the between 2.3 to 22.6 points. Let's get in the habit of comparing the before and after in this case. So you can use words like higher or lower, stuff like that. And we'll practice that again too. Notice our confidence interval does not contain 0. So because it doesn't contain 0, it means that mu sub d can't be 0. So does it contain 0? No. What does this tell us? That the mu sub d is tested not to be 0. And notice that this supports our hypothesis test. So it supports our decision to reject the null for this problem on the previous page. And then when we reject the null, we were saying that mu sub d, well here, let me back up. Our null hypothesis was that mu sub d is 0. And we rejected that. And now we could see that our confidence intervals supported that. Okay, so these next examples, we're dealing with raw data. So go ahead and pause it and see if you are getting the same answers. Come back and check your answers. And we'll look at this solution, and then we'll also do the same for the next solution. All right, let's see how we did. So the first one, we're doing a confidence interval. We're just going to alter whether or not we wear unimpaired vision or normal vision goggles first, just to rule out any confounding or lurking variables, because the second time you drive the course, naturally you'd be better at that. So we want to make sure that's not affecting our outcome. Put normal in list 1, put the impaired values in list 2, and it tells you to do impaired minus normal. So L2 minus L1 is an L3. Alternatively, if you don't like that, you could just go through and calculate these differences 9 times, put it in the list. And we're doing a confidence interval, so we're panicking. And these are our results. So pause it, make sure they look similar to yours. All right, and then finally we have our hypothesis test. We want to know if the new procedure is effective in reducing wait time, so we would expect the second column to be smaller if this was true. So L1, L2, I'm going to calculate the difference by doing L2 minus L1. So since this is supposed to be smaller minus a larger, I'm going to say the differences should be negative. So I'm making a left tail test. Alternatively, if you did L1 minus L2, it would be big minus small theoretically. So then L1 minus L2 would be greater than 0. So if you flip these, just make sure you flip the sign, and then everything will be the same for the most part. All right, so let's check your solutions. Pause it. Take a moment. And there you go. Okay, so L1, L2. Okay, so here's before, here's after. And then to get your calculator to do the math for you, you're going to go into this column and hit the up button so L3 is highlighted. Then hit second L1 minus second L2. And actually, this is what I had written, and I wasn't reading the problem close enough. I really should have done L2 minus L1. So all my numbers are going to be flipped. So this should be positive. So after that, hit enter, and it will populate everything for you. And then my signs are going to be off. And that's just how the cookie crumbles. Yours will be positive, so make sure you do it in relation to the test. Head on over to t-test. You guys are looking at data. And remember, it's difference data, so make sure your list is in L3 or wherever you guys decided to put the difference data. All right, and then you guys, we have our right-tailed test. Right-tailed test. You hit calculate. And then here's this. And again, I put in my data wrong, so I'm going to have some weird values. You guys are going to have that positive version. And then this is actually going to be 1 minus that value. But everything else should be the same.